So today we're also doing more volumes of revolution, but this time we're going to be doing cylindrical shells. So I'm going to take a region, let's say I borrowed this picture from the notes in the book, because it's actually a very good picture. So actually I'm going to take a region, as you can see, this region under the curve y is equal to f of x, and I'm going to revolve this whole region about some axis, let's say the x equals 0 axis or the y axis. And so I'm going to take a little region sliver and wrap it around. So when it wraps around, it actually gives me a cylinder. And then I'm going to stack all those cylinders up. And when I stack all those cylinders up, they're going to make a volume. Okay, so imagine you have a soda can and then you're putting those little rubber things on the outside of it to keep it cold. Then each one of those has its own little piece of volume. And so that's what it's going to make. Okay, so let's talk about how we're going to do this. So here's where what we said before comes into play. So if you remember, our original formula was the integral from A to B of the area of whatever region that we're revolving dx. So this area is a little bit different. Let's take and imagine that we took and we sliced our soda can straight up the middle and laid it flat. I see somebody has a hand raised. Yes. Question?
That was me. Can you hear me?
Yes.
That was me. It said you marked me absent. I just want to let you know I was here.
Okay. And you are again? I can't.
Ayana okay. Bugs.
Okay, because it says iPhone, so I can't see you. And I can't see your face. So
wait, why is my face not showing? Can you see me?
Now I see you. Yes, I see you now, Ayana. Okay. All right. So we have this region, okay, that's being wrapped around. It's still an area. So when I take my soda can and I slice it up the middle and I press it flat, that's the area that I'm looking at. So what is that area? Well, the area is the height of the soda can. So whatever this height is, so that's the height. And then I have to figure out, for this particular problem, I'm going to have to figure out what the actual radius is, because once I know the radius, then this length is 2 pi times the radius of whatever the circle is. So my volume is to take whatever this area is. Well, this area is 2 pi times whatever radius we get times the height. So that's what goes in my formula. So when I do volume by shells, my formula, so let's say I'm going to rotate around. So I have so if I rotate around a vertical line, okay, so a rotation about a vertical line is exactly this picture we were looking at up here. All right, so I have something that looks like this. I have some region, whatever it is. And I'm rotating about a vertical line. I'm going to find a line just like this. When I rotate the region, then the region comes over here, just like this. And this line appears over here from the rotation, and then it gets rotated like that. So therefore, there is my soda can. So once I find my soda can, whatever this function is right here, so this may be the function y is equal to f of x. So I need to find the height, which means I need to look for this piece, and then I need to find the radius. So for this one, very simple, I have something like that. So my formula is the volume is equal to the integral from 0 to 2 pi. No, that is wrong. It's the integral from a to b of 2 pi. Whatever my radius is, the general formula is x. And then f of x is the height. So now this is a very general formula because I never write the formula like this. This is the way the book writes it. I never write it like this because my radius is not always x. So here in this formula, my radius is x because I'm x units from the y-axis, and my height is f of x. But as you know, this is not always going to be the case. If I have the rotation about a horizontal line, then I would have something as such. So I may have some region and then I'm going to rotate it about the x-axis or this line. So now I'm going to find a value for y. Of course, that's going to appear on the other side. When I revolve it, oh, there is my soda can. Okay, and so now I need the distance here from the radius goes all the way up to y. And then my height is x, but here x is a function of y. So therefore I get that the volume, the integral from c to d of 2 pi, my radius and my height would be g of y dy. Again, the general formula. Because we're going to do some where that formula does not work. So as I said, the formula that Dr. Lott uses is this one. Of 2 pi, you must find the radius. You must find the height, dx. Or the volume, the integral from c to d of 2 pi times your radius times your height dy. Okay, so let's start. Let's do first problem.
And that equation will work for anyone,
This equation
any
that I
example.
just wrote, the equation I just wrote will work for anything. The other two are
Okay.
very specific. But this equation I just wrote, these two right here will work for any problem where you are doing volume by shells.
Okay, thank you.
Okay, so that is, so actually this is not, yeah, this is really not a general formula, I should say. This is actually a specific formula. Let me go back. Let's make this specific. The general formula is the one I put in green. So I'm going to call this specific because this formula is specific to certain problems. And I will show you what I mean right now. Okay. All right. First problem. The region.
I fucking dislike this fucking class so fucking much. Like,
What's that, Rashawn?
Hey, bro, mute your mic, bro.
Okay. The region bounded by the curve y is equal to the square root of x. I will write that in, comma, the x-axis and the line x equals 4 is revolved about the y-axis to generate a solid. Find the volume of the solid. Okay. All right, so the curve is y is equal to the square root of x. We've used this one before. And in fact, this one is going to look almost identical to the example from the book or the picture from the book. So here, I have the curve y is equal to the square root of x. So the curve looks like this. And the x-axis, so that's the bottom, and the line x equals 4. So if I draw x equals 4, you can all see my region. So that's my region. So when I revolve it about the y-axis, I get something like this. Okay, so I like to at least see when I revolve it, what it's going to kind of look like. So that's why I draw what it looks like. Okay, so now I'm set. All right, so now what I'm going to do is I'm going to pick an X. So I already know that here's an X in my region, and I am going to find the side of the cylinder or the shell. So there's the side of the shell at my arbitrary X. And then up my shell, because I'm revolving the side of the shell, the side of the shell appears on the other side. When I revolve it, there is my cylinder. So now that I've identified my cylinder, I need to find two things. We need to find the radius of the shell. Well, the radius of the shell is just the distance from the center of the shell to that line. And at that line, that distance is just X. So my radius is just X. And then I need to find the height of my shell. And the height of my shell is just this value right here, but that value is f of x, so the height is just the square root of x. Because any x, that height is its square root. So this is what we were talking about in some of the other problems, being able to identify what that value is. Okay, so now I'm done pretty much. I see this line, the line that I have, that's the side of the shell. Well, that line can start at x equals 0, and then that line can move all the way over to x equals 4. So this line can start here, and it can move all the way over to x equals 4. So once I've identified that, I now know that my volume, the integral from 0 to 4 of 2 times pi times my radius, which is x, and my height, which is the square root of x, dx. So this becomes 2 pi, the integral between 0 and 4 of x to the 3/2 power dx. And that integral turns out to be 128 pi over 5. So that one is by far, some people ask me, is that an easy problem, Dr. Lott, or would you consider that an easy problem? I would consider that one to be an easy problem. And the reason why I would consider that one to be an easy problem is because when I go to do everything, my radius is just x and my height is just f of x. So this falls into that specific category of the easier problem. Okay, any questions about that?
Dr. Locke, could I share my screen real quick?
Okay. All right.
All right. Can you guys see my screen?
Yes.
Okay, I just wanted to bring up that questions number 4 and 5 in the 2.2 homework make use of the things that you were explaining just recently.
Okay, but this is a volume by slicing, so I'm not doing any rotation about the x-axis for this problem.
Oh, okay.
So, yeah, I'm not doing any rotation for that problem. That is a volume by slicing problem, but it has no rotation. Okay, so the volume by slicing, if you remember, I'm going to go back because I was working with the student on this. With the volume by slicing, you have a base and you have these areas that are stacked up like Post-it notes. And you have to find the area of whatever the cross section is and move it back and forth. That's how you do volume by slicing. Volume by disk takes whatever region you have and rotates it about the axis. What we're doing right now is volume by shells. It also does a rotation about an axis. So I want to do a next problem, which is going to be.
I have a question, Professor.
Yes.
So, could you show how you got the, well, I know how you had to isolate 2 pi, but you got x to the 3/2. Now I understand the exponent would be a fraction because of the square root, but where did the 3/2 come from?
Okay, because this is x to the 1 times x to the 1/2. So you add those. And that's how you get x to the 3/2.
All right.
Okay, good question. You probably may not be the only person that didn't know what that was. Okay. All right, so this problem is going to be a little bit on the more difficult side. So I'm going to bump it up just a bit. So the region, oh, I forgot the right example. The region in the first quadrant bounded by the parabola y is equal to x squared. I'll write that in, comma, the y-axis and the line y is equal to 1 is revolved around the line x is equal to 2 to generate a solid. Find the volume of the solid. Okay, so this problem is certainly much more challenging. All right, so the parabola y equal x squared. So let's rewrite that in. Okay, so let's draw this. Again, note, the first thing I do is draw these things. If there's no picture, that means I expect you to be able to draw it. Okay, so everybody please draw this region for me. Draw the region. Elijah, turn on your camera. Edward. Uh-oh, why'd you turn your camera off? Oh, there you go.
What's wrong?
Nothing's wrong. I wanted to know if you are having difficulty drawing the region.
No, I'm good. I'm doing it right now.
Okay,
Okay.
good, no problem. Okay,
Dr. Lock, I assume you want us to draw the reflection for this, right? Or no?
yes, you may as well go ahead and draw the reflection. That would be good too. That would be excellent. Okay, anybody willing to hold their picture up to the camera? How about this? Everybody hold their picture up to the camera. Tiaja, I see you cannot.
I'm almost done.
I did
I
it, but
got it.
I'm kind of confused on how to reflect it on X.
Okay, Victor, I can't see, your hand was covering it. Okay, Gustavo, that looks pretty good, but you got to shade your region in. And I think you chose the wrong axis to revolve it about. Let me see, Victor, what you got. Okay, trying to see what other people have. All right, I don't see anybody else holding it up yet.
I'm holding mine up, but I don't know how to reflect it. I think I'm gonna reflect it wrong, so I was just gonna wait for you.
Okay, so hold on a minute. Who's that?
Q.
There you are. Perfect. That's beautiful. Okay, I love Q-Lay's picture. Okay, so let's start there. Okay, so we have y is equal to x squared. Then it says the y-axis and y is equal to 1. So if I draw y is equal to 1, that would look like this. And then the y-axis is just going to come down here. So I can see my region trapped in there very nicely. So that is my region. and it is trapped. Remember, this curve right here is y is equal to x squared. Okay, so now y is equal to x squared, and this curve y is equal to 1 intersect when y is 1. So this is where x is equal to 1. Okay, so that's very important for me. I know where x is actually equal to 1. Okay, now it says it's revolved about the line x is equal to 2. So let's draw that line. X is equal to 2. I'm going to draw it right about there. Okay, so here is my line. X is equal to 2. And this thing is revolved about that axis. That means I am literally flipping it over. So when I flip it over, give me 1 second. Okay, does everybody have their picture now drawn? So when I flip this thing over, this is 1 unit away. So therefore this will be 3. And this will be 4. I will have a line here like this. And then I will have something that looks like this. So this will go down like that to here. And then this will come across like that. And then this will be the other piece. And so the reflection of my region is right here. So that's the reflection of the region flipped over. Okay, so it gets flipped over the line x equals 2. Okay, so now I'm going to take and I'm going to pick an x between 0 and 1. Here's my x. And right there, I am going to draw a line. And it has to be inside the region. And of course, that line is going to pop up on the other side inside the region. And then it gets rotated like this. Uh-oh, I've got a little issue here.
Is that x equal, is that 4? When x equals 4?
This would be, over here would be x equals 4.
All right.
That's exactly what that would be.
I'm sorry, can you explain the rotation again? I don't know why I'm lost.
Okay, so I am taking a line like this, and I am rotating it around an axis. So when I have this line, that's the black line. And that black line is trapped between x squared and y is 1 right now. And when I rotate it around, it maps out the sides of a soda can. So that's where you see that. I don't know if you can see this red pen. So imagine that red pen, this being the top. That's the thing that's mapping out the circle, that black circle that I just did. Okay. So now I need to find 2 things. What do I need to find?
Radius and the height.
Okay, so I need to find the radius and the height. All right, so let's start with the radius first. One thing you must remember, this is x equal to 0. And this distance from here to here is x. But the radius of the circle is this distance. That is the radius. So how long is that piece? in terms of the X that you chose. So I'll give you a hint. Okay, so the distance from the X-axis looks like this. Okay, so this, I'm sorry, the Y-axis, this is X is equal to 0. Then the distance to X here, this distance is just a general X. So here, let me not write X equals 0. Let me just write 0. And this is some value X that we're considering. This value X is the thing that can move. So that distance is this red line right here. So that's that. And then this distance from here to here goes up to 2. Okay, so can you see it now? We're always measuring from 0.
So Dr. Lott, are we subtracting the distance from 0 to 2 and the distance from 0 to X, the general X?
Yes. So what would that be?
So
Would it be 2 minus X?
yeah, I was about to say, would it be 2 minus X?
It is 2 minus X.
Okay.
The radius of the circle is the green piece. It is 2 units all the way to the X equals 2. But where I chose my X to be is X units. So therefore, if I take this whole thing to, and then I subtract the X part, I'm left with the radius. So the radius is 2 minus X. So this is what I was saying to you. Not the radius is not always, it's not always X, f of X. That's a very specific case. When you start moving things around different and rotating around different things, it becomes different. Okay. So anybody that does not know the radius, okay, we took the whole distance from 0 all the way up to 2, and then we subtracted off the piece that went to X. And so therefore my radius is 2 minus X. Okay. That's the height. See the height of my cylinder? Okay, we're gonna do the same thing. This time you're looking at the Y value in order to get the height.
Y minus that 1 minus Y.
Okay, but what is the Y in the second one?
X squared.
Okay, and what was the first one again? This was, what's this line?
1.
Yes. Okay, so we're taking the whole height of 1, and then we're subtracting off X squared. Chule, you got it?
Yes, I got it.
I think I saw you get it. I think I saw you get it. Okay.
Yeah.
Maria, thank you. That was excellent. Let me see who else I can see. All right, Maxine, are you catching, did you get that? Or you need me to do it again?
Can you do it again, please?
I can do it again. Okay, so you see the pink is what I want, right? So the pink piece, did you just disappear? Did Matt, oh no, she's still there. Okay, so the pink piece is what I want, right? So I'm this high. I'm at y is equal to 1. So the pink piece is that tall. And then I know the curve is coming through like this, choop, 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 choop. And this is y is equal to x squared. So if I subtract, if I take the whole piece, y is equal to 1. And then I subtract the height that just goes to x squared, then it only leaves me that little piece, which is the height of the cylinder.
Okay, I get it now.
Okay, anybody else? Come on now. This is the time. Anybody else need explanation?
I didn't know that you could actually do the reflection halfway on the other side, because I was actually doing it as a compressed picture.
As a what picture?
So you see how you started off with like a single graph. So I didn't know you actually had to extend it in order to get
Oh
the
yeah, I just
reflection
had
of the
to,
other side.
I had to because I needed x equals 2 on the graph.
Okay, thank you.
Xavier,
Yes.
can you explain it back to me?
Well.
So I'm gonna give you, so let me show you this. Okay. Somebody asked you, Xavier, I need to know the distance from the top of your head to your knees.
Okay.
Okay. I need to know. So here's Xavier. I don't actually know how tall you are, but here's your knees. Okay. And I need to know the distance from the top of your head to your knees. So I only need to know this distance. Right?
Mm-hmm.
So if I know the distance that you have, how tall you are to the ground, and then I subtract off the distance from your knees to the floor.
Okay.
Then I have the distance from your head to your knees. Because I subtracted off. So the piece, so I took the distance all the way down to the floor and then subtracted off the distance from your knees to the floor. And then I got the distance from your head to your knees.
Wait, what would the numbers be in this case?
Okay, so the top right here in my picture is the line y equals 1. So this top is the line y is equal to 1. And then the bottom is the curve that's coming through like this at y equal x squared. So I'm going to take the whole thing, y equals 1, subtract off the part that is y is equal to x squared, and then that leaves me only the piece I want.
Okay.
So this is 1 minus x squared.
All right.
Okay. So now I can go back to my formula. Now, where does this X start? Let's see. Well, this line can start all the way over here and go all the way. I can take this line and go all the way up until X is equal to 1. So that line starts at 0. Okay. So therefore the volume, the line starts at 0 and goes to 1. I need 2 pi. We found the radius. It was 2 minus x. We found the height. It is 1 minus x squared dx. So that is what I have to integrate for this problem. And this answer comes out to be 13 pi over 6. Okay, any questions?
First, where do you get 0 from?
This purple line, the black line. So if you're looking at my, if you can see me on the camera.
Mm.
Okay, so this black line can go as far left as x equals 0 and still be inside the region.
Oh, okay.
And then it can go as far right as 1 and still be inside the region. Yes?
Yes.
Gotcha. Okay, so let me give you a problem tomorrow where we're going to start. We're going to do the same problem. We're going to revolve it around the region x equals -1. So I want you to have that ready for tomorrow.
You want us to have it like solved and everything? That's what you mean?
Yes, I'd like you to have it solved. Set it up, solve it. So when I do it tomorrow, it is review.
Hey, Dr. Lott. I just have a question on the first example.
Yes.
So for the 2 pi to the integral of 0 to 4 x to 3 over 2. So
the first
antiderivative. Yes. So I'm trying to find the antiderivative of x3 over 2. That's going to be 5 over 2 times 2 over 5, right?
Well, x to the 5 over 2, so it'll be 2 over 5. X to the 5 over 2 is correct.
Yeah, because I was nearly confusing that. I just needed to make sure.
Okay.
I wanted to make sure I did the steps so that way I actually understand the problem further rather than just writing the answer.